Today we're happy to have Matteo Braglia, who's been here since November, and he's going to talk to us about something about the CMB.
Yeah, something about the CMB and some signals from the early universe that we can test with the CMB. So actually, so it's going to be mostly a pedagogical talk. I will start. So the plan is to discuss all these points, but I'm not sure that I'll be able to get to the last one, which is actually the original results that are in this paper that I published in October. But the thing is that most of the physics is in point 1 and point 2.
They are in the shadow, your points, and invisible to you.
Sorry. So you can read it. Okay, I can read it for you. Anyway, the first point is about probing these signals that I will talk about using the CMB. And the second point is really the description of the physics which is behind the signals. Now, the reason I want to start from the phenomenological signatures is that I think it highlights the fact that these are not necessarily inflationary signatures. Okay, so I'm going to talk about signals from the very early universe before the hot Big Bang scenario. And of course, many people are biased towards inflation. I don't know anything about alternative scenarios. I've been working only on inflation. But what I'm going to, the testable predictions of the signals are probably the same as the very same signals but obtained in alternative scenarios. So the way we test it is essentially the same. And so this is why I decided to start from the phenomenology. And then, of course, this is the only topic I've been working on concerning the early universe. So I will explain how, within an inflationary context, we can produce these signals. Essentially, these signals are scale-dependent features in the primordial power spectrum. So this is the physics. And then, clearly, the original result is some new constraints, some new evidence, some new hints that the data give to these features. But this is going to be just a list of results. So all the interesting part is in the first 2 points. And if there is no time to discuss point 3, then if you're interested, you can ask me at the end of the talk. Otherwise, you can just check out my paper, which is called, by the way, Back to the Features. And the reason is that this topic here was more popular before Planck came, because essentially Planck, well, it didn't kill all these candidates, but no significant candidates for these signals was found in Planck. And so people got a little bit depressed about that, and people stopped working on that. But the thing is that with features in the experiments, as I hope I'll be able to discuss, we will be able to test and to rule out all the hints at these features or detect them if they are really shocking. Okay, let me start from point 1. So I presume that all of you know what the CMB is. Essentially, it is a background of photons that permeates the universe. It is in the frequency of the microwave. This is the reason of the name. And it was released when the protons and the electrons they actually combined for the first time into neutral hydrogen. And the scattering of photons, the compound scattering of photons became efficient, and so the photons were, ever since this redshift of recombination, actually the couple occurred a little bit later, but they were able to freely travel towards us. Okay, and the CMB is this path of photons that has a temperature which is 2.725 Kelvin, and again, at the first order, in the first approximation, it is homogeneous and isotropic, but we know that there are some very tiny direction-dependent anisotropies of the order of 10 to the minus 5 Kelvin, so very, very tiny. Okay, so we have some anisotropies in the temperature of this field, Now, at the surface of last scattering, some polarization was also induced. So these photons are linearly polarized. And the way we deal with this polarization is we take the Stokes parameters and we decompose them in E and B modes. Okay, so in principle we can map the temperature field, the E mode field, and the B mode field. Sorry, I think that the people on this side cannot see it, but anyway, it's E and B. And the polarization, these two polarization patterns are sourced by scalar and tensor perturbations. Actually, only the E modes are sourced by both of them. The B modes are sourced only by tensor perturbations. Primordial tensor perturbations are produced, are expected to be produced during inflation, and this is why sometimes, well, usually B modes are regarded as the holy grail for inflation. Okay. Now, what I'm going to, the idea that I would like to convey in this talk is that there are some things that we can learn about inflation or about the early universe in general without talking at all about B modes. Okay, so I will just focus on T and E modes. So what we do is the experiment produces maps of these two fields. Cosmologists usually like to consider the power spectra to compress all the information that is in the map in the angular power spectra of this map. And the expression for this power spectra, and this is the master equation for my talk, X and Y run over T and E. So I will only consider temperature and E mode polarization, is essentially the theoretical prediction for this seas of L is essentially given by this expression here. Now, what are these quantities? So P of K is the so-called primordial. This is a dimensionless quantity. Sometimes you see P and you see dk, k squared, but this is dimensionless. Is the primordial power spectrum of curvature perturbations. Okay, so the curvature perturbation is a gauge invariant quantity that is very useful because it's conserved for adiabatic fluctuations, of course. It is conserved on super-Rising scales. And so this is what allows us to connect the late time physics, and with late time now, I mean the hot Big Bang scenario physics, to the early universe physics, okay, whatever that was. And so this we compute for the early universe, okay, and this is the only place where the early universe enters in the computation of this seas of L. And then we have this transfer function that maps these primordial perturbations into what we observe today. And this encodes whatever late time physics that you like. So it could be the lambda CDM, it could be dark matter interactions, dark radiation, early diffusion, whatever you like that happens after the Big Bang enters here. Okay, so in order to understand what is the imprint of a scale dependence here, okay, we have to understand how these two guys behave. And we can start from the transfer functions that I drew before. Okay, so these are the transfer functions for temperature and for polarization at some given modules. Okay, so essentially at a fixed L, this is a function of K. This is log K. Okay, and this is, for example, I think this is L equal to 2, L equal to 20 or something like that. L equal to would be something like 1000, and so on and so forth. So what are the properties of these guys here? Well, first of all, you can see that the transfer functions, and they are all normalized to the corresponding maximum amplitude. Okay, so the amplitude that you see here is 1. So first of all, you see that they are strongly peaked. And the reason is that these are integrals over the line of sight of the source terms to the photon perturbations, convolved with some Bessel functions. So this is this means that a given co-moving scale in the primordial power spectrum would contribute mainly to L, which is roughly K times D star, where D star is the comoving angular diameter distance to recombination, and it is roughly 15,000 megaparsec. Okay, so there is a very easy way to understand the multiple to which a given scale would contribute to. Okay, and then in the following, I will take a very crude and very rough approximation for to build some intuition on the effect of these scale-dependent corrections that I will present in a second. And since these guys here are very big, I will simply make an approximation of the top hat function. So I will write down that TLXY is essentially TLXY max times a top hat in log K. Okay, so it will be something like this: log K minus log L divided by L peak, okay, plus some width, and the same with the minus. Okay, plus L star plus the very same delta. Now, if we model this transfer function in this way, what we see is that this delta is, of course, not a constant for every L, but first of all, it decreases as we go to larger multiples or to larger wave numbers. And we also see that delta EE at a given L is smaller than delta TT at a given L. Okay, maybe you cannot see it from this plot here, but if I were a good painter, you would see it, of course. Okay, and this is very important because this top hat approximation is useful to understand what are the features that we can see in the primordial power spectrum. Okay, so if we have something like this, if the power spectrum, and this is K, or better, it's log K. Okay, if the power spectrum goes like this, then of course we can see it. Okay, this can contribute to the size of L. But if we have some sort of very high frequency oscillations, then this frequency of these high frequency oscillations would average out in the integral. Okay, and we would only see the average. On the other hand, if the oscillation do not vary too fast, then this effect can be resolved. Okay, so this is telling you that since this is always smaller than this, in principle, E modes are a much better probe of the early universe physics than T modes. Okay, and this is interesting because, of course, Planck has mapped up to L equal 2500, most up to cosmic variance, the T modes, but the E modes are still limited by the experimental noise.
So this is always true regardless the top hat function.
Yes, this is always true. The top hat function is just to build some intuition, of course. All these things are computed numerically by Einstein-Boltzmann solvers. And but yeah, the reason I am explaining this, even if it's very pedagogical, is that when I started to study this topic a couple of years ago, I couldn't find any intuitive way to understand what was the response to these features, and so it's actually the appendix of my paper. It's not something new. It's just something that I believe is intuitive. So this is about the transfer function here. And then there's this guy here, which is the primordial power spectrum. So in the simplest scenario, the primordial power spectrum, actually, if is a function of this type. I'm not assuming any physics, I'm just assuming what the data require. So the data required an amplitude for the power spectrum and the tilt.
Sorry, can I ask about the previous point? So you're saying in E modes it's narrower. How much narrower? And is there a physics explanation also that you have for why it's narrower?
So it's yeah, there is a physics explanation. It's a little bit complicated, I think, to see it. At least I cannot give you a very short answer. But the reason is that these transfer, what are these? You should really understand what these transfer functions are. So what we do is we take the, okay, I will erase it later. For example, take the temperature. We have temperature, sorry, perturbations to the photons, okay? We compute, we convolve, these are really Fourier components. You could have temperature or polarization. Then you integrate out the angular dependence and you convolve them with Legendre polynomial, okay? And then you get the harmonic coefficients of these things here. And then the T, and then this can be seen to be an integral over the line of sight of the source that, so you have a differential equation for the evolution of these perturbations, and temperature and polarization have different source terms. If you compute this, you will have different, this is an integral over the line of sight. I have also the right expression, but anyway, you have some source term here that depends on the wave number, depends on the conformal time tau, and you have also the dependence on the optical depth, and you have something like this. And it also essentially it all boils down to the different source terms. So if you looked at this source term, you would see that these are more peaked. Maybe yeah, I think that is all I can say. And how much are they more peaked than this? Well, it's mostly this, I would say, that they decay. It's not really the first peak, the first oscillation, which is thinner. It is the fact that the first oscillation is much larger than the other ones. That, in principle, is telling you that you kill the contribution here in the tail.
Can just add a comment to this?
Sure, absolutely.
The temperature that you see today is sourced by the photon monopole, meaning the photon mean temperature perturbation, as well as their dipole, etc. So you start in the very early universe with perturbed photon monopole, and that oscillates. So you have them from the dawn of time. In contrast, the polarization is sourced by the photon quadrupole. And early on, in the early universe, when photons are tightly coupled to baryons, they don't have a quadrupole. They just have they're like an ideal fluid with just a monopole. So that's why the source term for polarization doesn't kick in until just around less scattering, so the sharper. Overall, there's the sharper region in redshift where it's lower.
And well, another thing that I didn't discuss, of course, I'm just considering TT and EE. You could also have the cross correlation. But for simplicity, I'm just considering the expression. Okay, back to the primordial power spectrum. So as I said, you need these two. Okay. You need this sort of parameterization to fit the data. So you need, and the reason is the following: if you compute the effect of if you compute how these two parameters show up in the series of L, okay, you have something like this. Again, the lnk transfer function, k, a s k divided by k star, and s minus 1. As I said, this this guy here varies slowly over the transfer functions, so it is essentially constant, and you can take it out. So this is telling you that this is what governs the amplitude of the angular power spectra. It is essentially what is usually called the Kobe normalization, and this is needed to provide the correct tilt. Okay, so it tilts the angular power spectra this way. Now the data constrained these two quantities to be roughly 2.1 times 10 to the minus 9. Okay, if you take the root mean square, this gives you 10 to the minus 5, which is the amplitude of the temperature fluctuations, and NS must be very, very close to 1, which indicates a nearly scale invariant power spectrum. Okay. Now, what are primordial features? So essentially, this is a near scale invariant power spectrum, but at least from a phenomenological point of view, we could allow some deviation from it. Okay, and some interesting deviations, and I will explain how they are motivated physically, could be simply something like a very small scale dependent correction. Okay, and for a moment, this is just phenomenological. We could define two types of corrections: sharp features or resonant features. For the moment, this is just a name. Okay, this is a correction of the form sine k divided by k naught, and this is a correction of the form sine omega log k divided by k naught. Here, k naught just simply shift the phase. Here, k naught is really the frequency of the signal. Okay, and then we can multiply them by either a scale independent or slowly varying scale dependent envelope. Okay, if the envelope varies slowly, then again this can be taken out the interval, so it's not really important for computing the correction to the cis of L. Okay, so what is the correction to the cis of L that we get from this?
What is omega?
Omega is a frequency of the signal. So if you plot this quantity here,
Omega log k is
sorry,
inside the
right.
sign.
It's
Okay.
inside the sign, but outside the log. Okay. So we can compute. We can get, using the approximation, the top hat approximation, we can really analytically estimate this the correction that this induces to the delta out, and well, maybe I can.
Sorry, can you tell us what are we doing? Are we trying to parameterize yet unfound signal, or we're proposing a theory for what this signal should
Yeah,
be?
what
I'm totally lost.
Exactly, sorry. So in principle, you could be agnostic to this, okay? So you could parameterize it with whatever function. Now I am anticipating what the signals that we should expect from the early universe, the form that they should take. Okay, but for this is by now just an oscillatory contribution to an oscillatory correction to this power spectrum. For the moment, it's just a phenomenological parameterization.
But what is your contribution? You will tell us how to detect those. You are proposing this form.
Now what I'm doing now is just since I don't know if you've ever heard of this topic, I'm just computing the response of the CMB angular power spectrum
for an arbitrary deviation.
For an arbitrary deviation from of the power spectrum.
And once you compute it,
and once I compute it, this will tell you what is to which scale, at which scale these sort of deviations will be better measured, at which scales they will show up. Okay. Then I will go to point 2, which is up there, which is predicting these features from the early universe, from features in the early universe. And then my contribution to the literature was in point 3, which is constraining these guys with with the
With the
real
actual
data. Right. But I think that, so I could have started from my contribution, but it's not really that interesting. I think that it's more interesting to explain why we can see them in the data, where we should look for them in the data, and why current data cannot detect these features. Is that clear?
Yeah.
Okay, I should have explained that before. Right, you're right. Okay, anyway, so now I want to compute the response of the CMB that we can see in the CMB. Okay, so this is simply CLXY minus CLXY bar, where this is CLXY bar. So the power spectrum, the featureless power spectrum, divided by, if you want to have a percentage, a residual, we compute this. Okay, this is just CLXY 1, and then this minus the zero component just gives this times this. We know that we can take this out the integral, so I will do it from the very beginning. AS K divided by K star and S minus 1 integral over D ln K DL XY K delta K. Okay, so in the top hat approximation, this, we take this out the integral. This integral here just gives DL max times the width of the top hat. So here we can multiply and divide by delta. We can assume that this is a top hat, so we have TL max xy here, and this is an integral over ln k peak minus delta divided by 2 plus delta divided by 2. So this integral can be solved assuming these two guys. And what we have outside the integral, well, this times this times this is essentially CL bar. So we have simply 1 divided by delta L xy. Now the result will change depending on which of these two features we want to consider. Okay, and it will change as follows. If we have a resonant feature, okay, so sine omega log k, the result would be delta L is equal to the amplitude, then we have log L divided by L star, and then it is multiplied by sine omega, where omega is the frequency, delta L xy divided by 2, this divided by omega delta L xy divided by 2. So at a fixed L, this, so you see the original contribution from the feature, but you see that as omega increases, so when we go to high frequency of the signal, this is suppressed. If delta L tends to 0, then this guy tends to 1, and so we recover the original signal. So in principle, if we had infinitely sharp transfer functions, we would see exactly the same primordial signal in the series of L, but of course we don't. And since, as I told you, the deltas decrease going to larger multiples, this guy, as we go to large multiples, goes to 1, okay? So this is telling you that the CMB, angular power spectra, are sensitive to this signal mostly at large multiples, okay? And you can see it from here. This is the primordial signal. This is the signal induced in TT, and this is the signal induced in ET. So this should look very similar, but if you look at the y-axis, you would see that this is roughly double the first one, the y-axis scale in the TT. Okay. So the lesson to learn is that for these signals, we should really look at large multiples. Of course, if we go to too much large multiples, we would have shift damping, so things will be complicated. But let's see, intermediate multiples. Okay, we should look for those signals. Now, what happens if we have instead sharp features, so oscillations that are linear with the wave numbers? We would have something like this. Now, the signal is much more complicated because we have that integral is a superposition of, a sum of sine integral functions, and it's something like this: E delta L2 minus psi E k naught minus delta L divided by 2 delta L divided by 2. Now, if we took the delta L to 0 limit, this again would be exactly the initial feature. So again, we would recover in the infinitely sharp transfer function case the primordial signal. We can take the omega equal to 1 divided by k naught to infinite limit. So again, we can try and check what happens for high frequency signals. And in this case, we would have something like this: C delta L divided by L naught, and what? Let's say cos k naught plus ta, ta, ta. So this is a superposition of oscillatory functions with the frequency of the original signal. Okay, this is actually an L divided by L naught. So the important thing is that in this case, we see that as we go to large multiples, the signal becomes suppressed. So depending on the running of the signal, we should look up for it either at large multiples or at small multiples. As you can see from here, as you go to large multiples, the signal becomes quickly suppressed. And this is the take-home message for the first part. Any questions so far?
Could you just clarify why there is a k in the delta L, like what that means if you integrate it over k?
So if you integrate it over k, this, and you assume that delta is given by sine k divided by k naught, recall that the measure is log k. This is integrated over log k peak. K peak or k star, as I said, is essentially this. Okay, plus delta divided by 2, and here you have minus delta divided by 2, and the result of that integral is this. These are sine integral functions. Okay, it's a complicated. A sine integral is a function that is something like this. And this should be, I think, pi divided by 2. This minus pi divided by 2. Okay, so for large arguments, it is an oscillatory. It is an oscillation. It is like sine x times some suppression. Okay, so if you expand for large arguments, then you get this.
Right.
The k should be k peak, right?
Yeah.
The k should be k peak, right? So it should be L divided by this. Okay. So the frequency in L space is not k naught, but it's k naught times the moving angular distance to recombination. Yeah, I'm going a little bit back and forth between k and L, but the thing is that you do induce a scale-dependent contribution to the C-over.
But that x-axis is really, we should think of it as a function of L, And it's just there's some corresponding K to that.
Right.
L.
This, sorry, maybe it's not really visible. This is what I wrote here. It could be either L of, I didn't set the ticks. So you could think of it either as log L divided by L star, where a star is just a pivot frequency, or K divided by K star. Sorry, just forget about the star. Either log L or log K. Just the ticks would change. The thing is that the primordial signal is in K space, and the signal we are looking at is in L space. But as you can see, I just wanted to stress that if you rescale either K or L in the correct way, you will see the very same frequency for the oscillations. 34 minutes, right?
What?
Sorry, I thought you were looking at the clock.
No, I was looking at the camera. It's yeah. We go to 1:30.
Okay.
So if you fit the current data with this correction, you get a better fit?
Yeah, that's 0.3. And I don't know if I will have time to say that, but sure, you get a better fit. The only thing is that the models, so as you can imagine from here, you have more parameters. You have an amplitude, you have a frequency, and you have a phase for all these parameters.
And what is the motivation for this form? It could be another
This is
form?
what I'm gonna say in 10 seconds. Okay. Okay, so point two, what are the motivations for these signals? As I said, I will just talk about inflation, but in principle, you should engineer similar signals also during other alternative scenarios, okay, from alternative scenarios. So what we do during inflation is we compute, okay, let me just review a little bit what is slow roll inflation, okay? So during inflation, we have this parameter, okay, which is the derivative of h over h squared, must be very small in order for the universe to accelerate, okay? Now this parameter, in the simplest models of inflation, where we have a scalar field that slowly rolls down a potential, okay, we could write down the Friedman equations, okay, and this would simply be given by the velocity of the scalar field, the kinetic energy of the scalar field, and this would be related to the derivative of the potential squared, and this would have to be much smaller than 1. This is the reason behind the name slow roll inflation, okay, because the inflaton has to slowly roll down the potential, and the potential has to be close to flat, okay, in order to sustain 60 e-folds of inflation. So we have that this guy rolls down here, okay? Now, what we do is that this is the background, okay? In principle, we have quantum fluctuations of this scalar field here. They would induce curvature perturbations. And we want to compute the power spectrum of these curvature perturbations on super horizon scale. So we can say at the end of inflation. Remember that during inflation, we have the conformal time goes from -infinity to 0, okay? So what we want to compute is this quantity here, P of k, which is equal to k to the third divided by 2 pi squared. This is just to make the thermal power spectrum dimensionless. And this zeta is the curvature perturbation, okay, at tau equal to 0. Now these are the mode functions for the curvature perturbation. The curvature perturbation itself is it's a real quantum operator, and it can be written, for example, as follows. It can be expanded using operators, where these operators here satisfy the usual algebra of ladder operators. Okay, and we have an equation of motion for these mode functions here, which is the so-called Mukhanov-Sasaki equation. Okay, so we know how to compute it. We know how to compute it in slow roll. It's very easy to do that. And this is the primordial power spectrum. Okay, And what we do is, again, this. Okay, so this is the slow roll mode function. So I should really write primordial power spectrum here and slow roll. And this, if we do the computation, takes this form, okay, ns minus 1, where ns is essentially equal to 1 plus linear combination of epsilon and the derivatives of epsilon with respect to time. Okay. Now, as I told you, epsilon is small, and so this is why slow roll inflation predicts a near scale invariant power spectrum. Okay. Now, what we want to compute is the effect of primordial features. Now we get to the physics of primordial features. What are primordial features? Okay, primordial features are essentially some small disturbances to the attractor slow roll solution. Okay, so you could just think of them as small corrections, time-dependent corrections to the background, sorry, to the leading order slow roll epsilon. Okay, just to give you an example, a primordial feature could be like a spike in the potential. If you add a very small spike here, then this would produce a correction to the epsilon. So for example, if it is a spike, it could be just an amplitude, the amplitude of the spike, times delta tau minus tau naught, where tau naught is the position, is the time at which this phi crosses the spike. Okay, this could be an example. And how do we compute the correction induced into the primordial spectrum due to this feature? Well, there is a technique to do so. It's called the informalism, okay, which is the way we compute the inflationary correlations. It's a generalization of the so-called in-out formalism, which is what is used in quantum theory, okay. And I will skip the details, but essentially the correction, I call it, okay, it goes as follows, okay. The formula is the following: 1 divided by epsilon slow roll, imaginary part, this guy is not here, of dx, x is equal to tau divided by tau naught, x0 is defined as k tau naught, e to the 2I x naught, and this is the most important factor here, delta epsilon of x times, well, some polynomial factor which is not really important for the discussion. This is an I, and then we have 1 x naught. Okay. So what happens if we have, for example, a delta here? Okay. Written in terms of this variable, this is just delta x minus 1. Okay. So if we put a perturbation like this to the influent potential, we have a delta here integrated over x. We simply put x equal to 1 here, and so we have a correction that is essentially an amplitude times e to the 2I x naught. Now, x naught, as I said, is equal to k L0. So this is why I called that guy over there, I think it's, where is it? This one, sharp feature. Because if you add a sharp feature during inflation, so something that happens on such a short time range that you can approximate it as an impulse, as a delta, you get essentially a correction to the power spectrum which is a sinusoidal function with a frequency which is set by tau naught, which is essentially the inverse of the scale that crosses the horizon at tau naught.
This seems very arbitrary to me. Why not a step function? Why not a
Right.
sine function? Why not a whatever? Seems like totally
Sure.
arbitrary.
I'm going to discuss that. For example,
How
what
can you
happens-
discuss it even?
well, it's a little bit arbitrary. You're right, but the thing is, if you model this as a bump, for example, okay, you wouldn't have a delta. You would have something like a Gaussian profile, and so this would change. You would still keep this running, but then the amplitude would be modulated by like a Gaussian envelope, e to the minus x naught squared divided by alpha, where alpha is the width of
That's
this.
exactly what I'm saying. It's
Sure.
totally arbitrary.
And if you put a step, then this is even more arbitrary. I agree. But this at the same time, if you are able to detect this and to tell apart different envelopes, then you might get some hint that this arbitrariness it's actually what was happening there.
Can I ask a question about the physics here? So if I have this bump case,
Mhm.
right, why doesn't the field get trapped there for a while and then only later escape by tunneling or going over the barrier by thermal fluctuations? I mean, and then you get the physics very much like was discussed by Guth and Weinberg, famously for original Guthian inflation.
Right.
So it's not at all clear to me that you can model the perturbations you get by this kind of expression here. This seems there's no sign of tunneling or thermal jumping over the barrier. Where is that in this formula?
Yeah, I totally agree. I didn't discuss one thing. So the thing is, this delta epsilon must be much, much, much smaller than this. Okay, and actually, if this is the case, there have been works saying that this tunneling, essentially, the tunneling rate is negligible because you don't really need the tunneling. I mean, the inflaton just doesn't get trapped. If the inflaton gets trapped, of course, you would need to compute all these things.
And that would be ruled out by observations immediately.
That would be ruled out by observations, of course.
That's not clear to me because clearly there's a sort of limit. I mean, there's a limiting case. I take this bump where I'm trapping, and then I take the bump smaller and smaller and smaller. I take the delta function, and I make the tunneling fast enough that I just get small Guth-Weinberg-like perturbations. It's not, but it's still different from this in form.
Well, but this is okay. Let's put it another way. Yes, it might not be ruled out by the observations, but I'm pretty sure that the signal that we would observe in the primordial power spectrum would be different from this. And so, in a reverse argument, you could use the observations to tell whether there was tunneling or not, if this is really the case, if the signal is different from this.
Yeah, so it goes back to the
Right.
question, which is,
Right.
what is the motivation? What is the correct way of parameterizing reasonable deviations? Right.
Yeah.
We have to think about
Yeah. So the
And
thing
what-
is, this is. It's most of.
Doesn't fundamental physics have some ideas about the reasonable things that can happen during the
Right.
inflationary?
No.
It's called a Taylor expansion.
Yes.
Why is this the parameterization?
Yeah.
Why is this an interesting parameterization?
Well, this is an interesting parameterization in the sense that, well, first of all, I jumped in this business like last year or a couple of years ago, and there were already a lot of papers on this stuff. So I trust them, the big guys who did this thing, which is not probably the best thing for a postdoc. But anyway, well, let's
The
put it
big
a different
guys
way.
are already dead.
The big guys are already there. I agree. But anyway, if your tailored parameterization looked like something like this, okay, then this is what you would get. Okay, if by Taylor expanding your potential, you would get something like this. And also, this is not the only perturbation that we can have. For example, we can have something like there are models of, for example, monodromy inflation. I don't know what are the theoretical motivations behind those models, but they quite generically produce something like this, a sine perturbation. Now, this would give a completely different phenomenological signal. It wouldn't be a sine k divided by k naught, okay? But if you did the computation, you would find this signal, a resonance signal. So it would provide a signal that runs with log k, okay, not k. So it's a different thing. Or you could imagine, now this is a single field inflation, but you could also imagine multi-field inflation, okay? Now, if what we usually think of could also be seen as a straight, so slow roll inflation could also be seen as a straight line in a multi-field manifold, okay? Suppose that you have something like this, okay? You have two fields, you have a straight line, and this is like the bottom of a potential. You have the orthogonal direction are stabilized because we are at the bottom of a very massive potential here. But then you could have like a turn, okay? If this turn occurs on a very short time scale, then it would behave as a sharp feature, and you would say something like that. Or you could have even more funny things like you have a straight line here, then you have a turn again, but instead of getting back to a straight line, you enter a curved path of valley. So what happens is that you excite, still supposing you are at the bottom of your potential, you excite some heavy direction, some heavy field, okay? You have a sharp feature, and then this excites a small correction to the background, which it is a sinusoidal correction to the background, and it has the frequency that is essentially the effective mass of the field you are exciting, okay? So you have, at large scales, a sharp feature, and then at smaller scales, you have a resonant feature, okay? So if you were to observe this, it would be a unique signature that cannot be mimicked by other physics. I'm not saying that this is whether this is fine-tuned or not, but it provides a clear signal of some non-standard physics. Now, whether this is fine-tuned or not, I've never thought about that. I probably should have, but it is a well-posed problem from the point of view of detecting these signals in the CMB. Now, probably the most agnostic thing that one could do could just be to be really agnostic to this, okay? Parameterize it as a spline or whatever, and reconstruct it from the data. This is another approach. This is a model-independent approach that has been pursued by many people. But the thing is that, first of all, you really don't know whether that could be described by some sensible physics. And you always have to make an assumption in the parameterization. And you might miss also some high-frequency oscillations. I don't know. Usually you need a lot of parameters, whereas if you assume already a parameterization, you need only a handful of them, like 1, 2, and 3. So the significance of template search, such as this one, is usually much larger than, much higher than the one from agnostic searches. And this gets me to point 3. If you don't have any other questions, I have like 4 minutes. So what are the data really telling us, which is the real question? Do we see hints of might be primordial features in the data? Now, the thing is, as I told you, this is a really powerful proof, but Planck hasn't measured E modes up to the same accuracy to which it has measured T modes. So all the hints at primordial features, nowadays, they only come from temperature. Okay, so E modes essentially is constraining more these features, is helping constrain these features, but it is not hinting at any feature. So I would try and make an effort to draw the residuals from Planck. So here I am plotting L plus 1 CLT. So what people do in the business of the CMB, they plot different scales from L equal to 30 up to higher multiples and at very large scales. Here I am plotting linear scale, and here log scale. This is the CMB temperature power spectrum, and these are the residuals. Okay, so going from very large scales, the Planck data look more or less like this. Okay, so the data points. Okay, this is a delta D L. Okay, so these are the data points. Okay, so at very large scales, up to I would say L equal to 10 or something like that, all the data points, they lie below the zero. Okay, so we have some hints at a suppression of power. Now the problem is that here we are really cosmic variance dominated. So the errors induced by cosmic variance are very large, and so all the error bars very naively they touch zero. So this is not a significant feature, though it was already observed by WMF. And so they go up.
Yeah, but I mean, there's more strange things about those low multipoles, which is there's a commonality of alignment among those deviations as well. And so you get this.
No, maybe I'm not sure they are aligned. You mean that they are going in the right direction?
No. I mean aligned in the sky.
Oh, right.
Yeah, you know. So if there's more information than just this, just the deficit in power in each of the odd poles, it's relative orientations, position of the sky.
Right.
And that's also fairly significant. There was a whole bunch of papers came out, whatever, 10, 15 years ago, like Axis of Evil, describing.
So we should let Matteo finish now, because that is a whole nother.
Well, anyway, I mean,
strange.
it's still 5 minutes, right? I should have. Okay.
Well,
anyway,
it's 1 minute.
Let me go very fast.
We'll give
And
you
then-
time to.
Okay, and then we have something like this, okay, around L equal to 20, okay, which can be seen more or less as the same suppression, but it matters quite a lot when it comes to finding candidates from feature models, okay, and this is more significant, okay. It goes, I think this at L equal to 20 is at something like 3 sigma, still it's, or 3 sigma-ish, it's still an anomaly, it's not a tension, of course. And then it is interesting to see what happens here. So all that we see here was also detected by WMAP. I mean, it was seen also in WMAP, which is what makes it interesting. Okay. Then Planck measured the higher multiples much better than WMAP. So what we see here, it doesn't have a cross check from other experiments, except from, for example, ACT or SPT. The only problem about SPT or ACT is that they haven't released any unbinned data set, and we have very high frequency oscillations, so we cannot test these high frequency oscillations with unbinned data. We have something like this, and you try to fit it with this, it doesn't make sense. But with Planck, we do have unbinned data, and the residuals, and you can see some like oscillatory pad of the residuals, okay, some more oscillatory pattern. It is not statistically significant. Now, the only thing which is a little bit significant is around L equal to 750, and we see something like another dip. This doesn't reach, I think, 3 sigma, but it's between 2 and 3 sigma, and this guy here is indeed also observed by ACT, okay? And yeah, I think I'm running over time, but different mechanisms, okay? So for example, back to the initial question. So if you had a step here, the only place you would be able to fit the data is this dip here, because of the specific shape of the envelope, okay? Because you would get something like this as your delta K, okay? If you add instead some oscillations in the primordial power in the potential, you will see something like this, and so you would be able to fit this here, this guy here, and some oscillatory residuals, and so on and so forth. Each model has its own delta chi-square. Each model has its own evidence, and what I did in this paper here is to really scan all the models that were proposed in the literature. Some of them I invented myself with a lot of arbitrariness, of course. and provide which are the targets for future experiments. And it happens that with future experiments, we would be able, if these are real hints, to rule them out or to detect them, okay, with very high statistical significance. And with the future experiments, I mean only CMB experiments. Of course, there are a lot of other cross correlations that one can do with the last gauge factor, 21 centimeter, etc., but I'm not an expert of that. Okay, it's 1:30. Thank you.
So we have time for like one question or go ahead.
Up front, you dropped the beam modes. I missed the point. Why did you drop the beam modes?
Not because, I mean, because the thing is the following. We don't need beam modes to detect this feature because it's a feature in the scalar sector, in the scalar perturbations, and scalar perturbations do not induce beam modes. So these signals will show up only in temperature and E modes. Of course, when you build a model explicitly, like the proposals that I made, then you would compute also your B modes. And if the model, for example, one model that affects also the B modes is the so-called Starobinsky model, where you have an initial phase of fast roll. So essentially, you have that the slope of your potential before and after the feature is different. Okay, so it goes up like this. So your potential, sorry, your scalar field runs much faster, rolls much faster before the feature, and this modifies also h, the background value for the Abel parameter, and so you would be able to see that also in the B modes. Okay, you would see a bump at large scales in the B modes, which could be a potential signature of this model. But yeah, for the purpose of my discussion, I didn't need B modes.
All right, let's thank Matteo again. Because I screwed up the event thing, I'm not sure whether or not we have cookies. We might not. Apologies if we don't.
Thank you. Matteo, sorry, my hand is I'm here.
So if you implement this thesis, that will